going to continue our discussion of increasing functions, decreasing functions, maximums, and minimums. Okay? And so I think we've began the idea, or we started the discussion last time. Let's go ahead and just look at some more examples here today. Just some different situations, different than the one that we did last time at the end of class. Okay? Let's take a look at this function. F of x equals x plus 3 divided by x minus 4. And our goal is to identify where is this graph increasing, where is this graph decreasing, and then today I'm going to add on, are there any maximums or minimums? Okay, we didn't quite get to that last time, but we'll go ahead and add that on here today. All right, when we solve problems like this, when we're interested in finding increasing, decreasing, maximum, and minimum, the first thing that we have to identify are what we called last time critical numbers. We have to pick out where these values are at because these are the possible places where it could be changing from increasing to decreasing, or vice versa. Where were the two places we could find critical numbers last time? Where's one of the places we get critical numbers? Okay? Any place where there's a discontinuity in the graph. So if we have any jumps, any asymptotes, any of those types of things, that is a possible place where we could change from increasing to decreasing. Okay? Do we have any of those on this graph here? Do we have any places where we will have a discontinuity? Yes. Where is it at? What's the one number we cannot sub into this equation? 4. We cannot sub in 4 because that will give us division by 0. So we have one critical number already at x equals 4. All right. Second place we can get critical numbers. Where are those at? Where the derivative equals 0. So this one's going to take a little bit more work because we need to actually calculate the derivative and then set it to 0 and see if we get any solutions. Okay? All right. When I look at this function, what rule do I need to use to take the derivative? You need to use the quotient rule. All right. So let's run through the quotient rule here. Let's see what we come up with for the derivative of this example here. All right, the quotient rule says I need to take the derivative of the top times the bottom. So what's the derivative of the top? Yeah, 1 times the bottom. Okay, minus, and then I switch that order around. Then I take the derivative of the bottom times the top. Well, the derivative of the bottom is 1 times the top. And then I divide by the bottom piece squared. I'm interested in setting this equal to 0, and as we look at the numerator, of course multiplying by 1 doesn't really change anything. What cancels off, and then what's left? Well, I see here I've got a 1x, and here I've got a negative 1x, so those are gone. The only thing left up in the numerator is a negative 4 and a negative 3, so it looks like negative 7. All right, now, as we look at the situation that we've got, we've taken the derivative, we've simplified it, we're down to this point. Can this function ever equal 0? What's true about any fraction? If we ever want the fraction to equal 0, what has to be true? Yeah, the numerator has to turn into 0, correct? If I'm going to have a fraction that equals 0, I need to have 0 divided by something. And it doesn't matter what the bottom is. If the bottom's a 5, I still get 0. If the bottom's a 20, I still get 0. Okay? So I can ignore the denominator. It's not going to impact me anything in any way here. Can this numerator ever equal 0? No. Negative 7 can never equal 0. And all that means for us is that we just didn't pick up any more critical numbers here. Okay? We picked up one critical number from here. We just didn't pick up any more from here, and that will happen from time to time. Most of the time, you will pick up more critical numbers from the derivative, but we didn't know that when we started. Okay? All right, so the only critical number that we ran across in this situation was x equals 4. So that means I want to take my number line, and I'm going to split it up into different regions. The only place where I split it up is at this critical number 4. So the first region will go from negative infinity all the way to 4, wherever 4 is at on the number line. And then the next region will go from 4 on to infinity. I only have one split this time. Now, how do I decide if the graph is increasing or decreasing in here? Okay, very good. Just pick a number from this region and sub it in. Now, here's my question. Do I want to sub it into the original, or do I want to sub it into the derivative? Good. I want to sub it into the derivative. The reason I want to sub it into the derivative, okay, if I pick a number in this region here, if I sub it in the derivative and it's positive, what does that mean? What happens if you have a positive derivative? Positive slope, it has to be increasing. Right. That's why I sub it into the derivative, because I'm checking for the slope. Okay? All right, what's a nice number here? Well, probably 0 is a nice number to pick. Okay, if I pick 0 and sub it in here, the denominator is what kind of a number, because it's squared? Positive. Negative 7 over positive is negative, so what's happening in here? Decreasing, right, okay, because I get a negative slope. If I pick a number in this region and substitute it in here, what type of result do I get? Same thing, right? It's also decreasing, because again, no matter what I plug in here for x, as soon as I square this, it's always positive. And if I take a negative divided by a positive, that will be negative. So this will also be decreasing. Okay? All right. On this example, I won't have any maximums or minimums. Now we didn't have a good example to talk about this on here. But when you're in calculus, when you get a maximum or a minimum, you get a change from decreasing to increasing or vice versa. You know, for example, don't change this in your notes, but had this been increasing, if I have a graph that's decreasing and then all of a sudden it changes over to increasing, what had to happen down here? Has to be a minimum value, doesn't it? Okay? So whenever we get these changes from increasing to decreasing, that's going to be our clue that we've got a maximum or a minimum at this location, 4. Okay? Well, this time we didn't have a change. It continued to decrease, and so we don't have a maximum or a minimum here. Okay? What is happening at 4? Well, we already said that was a vertical asymptote, didn't we? It was a discontinuity. Okay? All right, so this problem is finished. There wasn't a whole lot in this problem because we didn't have very many critical numbers. Okay? All right, let's consider another example here. Y equals x minus 4 times the natural log of 3x minus 9. Okay, we'll see how this one works out when we've got a natural log function in here. Okay, I start by making a list of critical numbers. Okay, are there any numbers that I cannot substitute into this equation? Well, first of all, I don't have any division, so I don't have to worry about dividing by anything to come up with 0, so that's not a problem. I do have to be a little careful with the natural logarithm function, though. The only types of numbers that I can sub into a natural log function are numbers where this stuff in parentheses is bigger than 0. Okay, I can't take the natural log of negative 2. I'll get an error message. Okay? So what's the smallest number I can plug in here for x to keep this bigger than 0? Because if I sub in 1, I get 3 minus 9, and that's negative, so that's no good. What's the smallest number here? Anything greater than 3. If I sub in a 3, 3 times 3 minus 9 would give me exactly 0, and so that would still be a problem because we can't take the natural log of 0. But if I plug in anything bigger than 3, then I'm okay. So kind of off to the side, I mean, it's kind of a critical number. Okay, but it's more of just a domain for this problem. X has to be at least 3. So if we get any critical numbers smaller than 3 later on, we can toss them out because they're not even going to work in the original equation. Okay? All right, second critical number is where the derivative is equal to 0. So let's run through this derivative here. dy dx. All right, what's the derivative of the first term? 1. Okay. What do I do when I have multiplication times some function? What happens with the 4? Just kind of stays there, doesn't it? Okay, it's part of the derivative. So the 4 stays there because it's multiplied. Okay, now, what's the derivative of the natural log of something? Okay, the derivative of the natural log of something is 1 over the something. So 1 over 3x minus 9. Now I look inside the parentheses because I'm done with the natural log part of the derivative. And what's the derivative inside the parentheses? It's a 3. So I have to multiply this by 3. Okay, so here is my derivative. I want to set this equal to 0 and see if I come up with any solutions. Now, here's where your algebra comes into play. Let's see if we can clean this up here. How can I write this as just one fraction? What needs to be up in the numerator? Okay, I could put a negative 12 up in the numerator, or I can leave the subtraction out here either way, right? Okay, but definitely a 12 coming from 4 times 3 is in the numerator, and then this 3x minus 9 is in the denominator. Okay, so just an algebra skill, we have to be able to do this. Now, how would you solve this for x? And there's not just one way to go here, but what's one thing you could do? Okay, heard a couple of things here. One of the things that could be done is we could subtract the 1 as one possible first step. So we'll go ahead and do that. And then from here, I heard another possible first step was, now let's go ahead and multiply by 3x minus 9. Okay, so let's go ahead and do it this way. So negative 1, 3x minus 9. So I multiplied, basically cross-multiplying is what I'm doing here. Get that denominator across. Okay, now I just have to go through, distribute, clean up, and then solve the rest of the algebra problem here. Okay, all right, so here, I'll bring this up here. I've got negative 3x plus 9 equals negative 12. And then algebraically, if I subtract 9 from both sides and divide by negative 3, it looks like I get a critical number at 7. Okay? Do we want to keep that critical number? Is it useful for us? And the answer is yes, okay, because it's bigger than 3. All right? Now, the difference on this problem as compared to the previous one is that when I set up my number line, instead of going all the way back to negative infinity, I should only go back how far? Yeah, I should only go back to 3 because I can't have or can't substitute in any number smaller than 3. So that's the difference in this question, is that I just don't go all the way back to negative infinity. Okay, so I start at 3. My only critical number is 7. So I go from 3 to 7 and want to see what's happening in there. And then I go from 7 on to infinity to see what's happening in there. Okay? All right, so if I pick a number in here, well, 5 is right in the middle, so let's go ahead and choose 5. If I was to sub 5 into the derivative, what type of answer would I get? Okay, and of course, we're not setting it equal to 0, we're just subbing it in. Okay, if I sub in a 5 down here, the denominator is what? 6. 12 divided by 6, 2. 1 minus 2, negative. That's the key. Okay, so if it's negative, what's happening in here? Decreasing, right. Okay, so the graph is decreasing from 3 to 7. Now let's see if we get a change once we get past 7. Okay, maybe I'll pick 10. Usually a nice number. Okay, 3 times 10, 30 minus 9, 21. Okay, 12 divided by 21, not necessary that we figure it out, but what's going to happen when I take 1 minus 12 over 21? What type of answer is that? Careful. 12 over 21 is not a full unit, is it? So if I take 1 minus a part of a unit, I'm still a positive value, aren't I? Okay? So this is a positive value, which means that this would be increasing over here. Now, of course, you can actually plug this in your calculator if you want to double check. Okay? But really the key is that we just need to know it's positive. So if the graph was decreasing, it got to 7 and then it started to increase, what's happening right at 7? Yeah, it's like the bottom of a parabola almost, isn't it? It is a minimum value. And so this is what we can say is that at x equals 7, it looks like we have a minimum on this graph. Because it was going down, it hit 7, and then it started to go back up. Okay? And so that's how all this stuff ties together. We go ahead and find our critical numbers to help pick out decreasing and increasing, and then whenever we get a change, we look at, well, was it a minimum or a maximum? Okay? All right, so there was that question with the natural logarithm in it. Okay. Let's do another example here. All right, we've got y equals x to the 1/3 plus x to the 4/3. Again, trying to pick out where the graph is increasing, decreasing, and if there's any maximums or minimums on this graph. All right, so I make out my critical number list. All right, are there any numbers where I have a problem to begin with on this? What is 1/3 power the same as? Which root? Okay, third root or cube root. Okay, if I have a cube root of x, can I put any number in there? And really the key is, can I put negative numbers in here? Can I take the cube root of -10 or -20 or any of those? And the answer is yes, I'm okay doing that. Okay? Now, if you ever question yourself, you just plug one in your calculator and you try it. Plug in cube root of -20 and see if you get an answer or an error message. Okay? But I can take the cube root of negatives. If this was a square root, then I would have a problem. I would have to make sure x was bigger than 0. Okay? This is also a cube root type graph, so I am okay. I don't have any domain problems. I don't have any discontinuities on this graph. Okay? So first critical number, or for discontinuities, I didn't pick up any critical numbers. Okay? Now I go for, where's the derivative equal to 0? All right, so let's take dy dx for this thing. All right, what's the derivative of x to the 1/3? One-third x to the -2/3. Good. Okay, I need to subtract the full unit off of 1/3. Okay, what about the derivative of x to the 4/3? 4/3 x to the 1/3. Right. Again, I just take a full unit off of 4/3 and I'm back to 1/3. Okay. The reason I wanted to do this example, not that the derivatives were really difficult, but the problem is now when we try to set this equal to 0, what do we do in a situation where we've got negative exponents and positive exponents? How do we solve this for x? Okay. If I gave you a problem, 2x to the 4th plus 6x, to the 5th, for example, okay, how would you factor over here? Okay, definitely you would take out a 2, wouldn't you? Okay. And then what else can we take out in terms of x's? X to the 4th. We can actually take out 4 of those x's, right? So my point being here is we look for which number factors out, but then we also look for the smaller power of the 2 that can be factored out. Okay, now if we come back over here, first of all, what can I factor out in terms of a number? I can take out a 1/3. Now, which of the two is the smaller number? The -2/3. So I actually want to factor out that smaller factor, -2/3, just like I factored out the smaller one over here. Okay? Now, the question is, what is left in here? What's left that I need to multiply by so that this matches up with this? Just a 1, right? Okay, because I factored out everything. What do I need to multiply this by so that it turns into this? Well, first of all, what number? How many 1/3 are in 4/3? Well, there's 4 of them, right? Okay, so I need to multiply by 4. Now, this will be the hard part here. If I come back over here to this example, I have a 1 plus. Okay, how do I know how many x's are left here? Okay, because I need 5 of them and I've already taken out 4. So in my mind, what I'm doing is I'm really taking 5 minus 4 here, right? We would just see that it's x to the 1st, but in your mind you have to subtract this number minus this number. Okay? Same thing needs to happen over here. We need to take the larger power minus the smaller power. Okay? And so again, off to the side, I take the larger power minus the smaller power. Notice there's two negative signs on this one. So it's addition. What's 1/3 plus 2/3? 1. So this actually turns into just an x to the first over here. Okay? So the point I'm trying to make with this example is factor out the smaller number and then do a subtraction to see what you need to fill in that last spot. All right, now we want to set this equal to 0. Okay, let's see. What solution do I get from this first factor here? And this is a little tricky on this one here. I've got a 1/3, I'm going to rewrite it this way, with a positive exponent in it. Okay? Can this ever equal 0? Can this fraction ever equal 0? No. Okay? Just like that example we had before where we had a -7 on the top, can 1 ever turn into 0? No. So I don't pick up any solutions from this first part. Okay? All right, what about from the second part? Can the second part ever equal 0? Looks like it. Yeah, this looks like a solvable algebra equation. We would subtract 1 from both sides, and then we would divide by 4. So it looks like my critical number from the derivative is -1/4. Okay, so something is going on at -1/4. Okay. All right, in terms of our number line, again, this will be a pretty simple example because we only have one critical number. Okay, I'm going to go from -infinity to -1/4, and then from -1/4 on to infinity. Okay. All right, I need to pick a negative number. Probably the easiest one to choose would be -1. Okay. If I come back into my derivative and I plug in -1, what type of answer will I get? Okay. All right, if I sub in -1, what's -1 to the -2/3? And if you need to punch it in your calculator, you can, or you can just look at it in here. What if I put a -1 in down here? What's -1 to the -2/3 power? Should be +1. Okay? The reason it's +1 is because, I take the cube root, but then the next thing I do is I square. And whenever you square something, that's positive. Positive number times 1/3 is positive. Okay? So it looks like this is positive. What if I plug in -1 here? What's this factor? -3, right. So a positive number times -3. So the whole product is what? Negative. And so what's happening in here? Decreasing. Like I said, I'm doing this in my head here. Some of you will be able to do this. Others, you may just have to plug in the numbers. Just start punching them in your calculator and see what it is. That's fine. There's nothing wrong with that. What if I pick a number from this region? Well, I'll go ahead and pick 1. Okay? What if I sub in a 1 in here? What type of result will the first factor be? Be positive, right? Because everything's positive in here, so this is positive. What if I put in a 1 over here? It's also positive, right? It's 5. Okay, so positive times positive is positive. So what's happening in here? Increasing. And so therefore, what is happening at -1/4? It's a minimum value, isn't it? Because it was decreasing and then it changed over to increasing. So x equals -1/4 is a minimum value. Now, I want to point out one more thing in terms of just how the answers may look in the back of your book here. Okay? We figured out that the minimum value occurs when x is -1/4. A lot of times when books talk about a minimum value, they may not be talking about just the x-coordinate. They may also be talking about what's the y-coordinate. They want to know what is that lowest value on the graph. And so the minimum value that they may be looking for is when you take -1/4 and you sub it back into the original and get that answer. So if you go back and look in the back of the book and you've got this for your minimum, be careful. Maybe they've got the y value listed instead of the x value. Okay? To be safe, just go ahead and list the whole ordered pair and then you've got it. Okay? All right, that takes care of our discussion then for today.